where we left off on Tuesday is we were talking about both a little bit of the mechanics of shaders as well as the architecture associated with it. And there's a lot of good architecture questions. I think we sometimes suffer in a class like this from there being relatively less interesting documentation about low level graphic shader architecture versus when we do start to talk about compute view of things. There's a lot better documentation for how the compute side of things is organized. Um, and so you'll see some things are kind of left as it's hard to say in terms of answers for some of the questions. But then I think we'll get past that. I do think though for teams to be successful in MP3, making sure we have a decent understanding of just the mechanics of shaders is also pretty helpful, and it's a necessary step. I saw that a lot in the lab yesterday. Teams who are making good progress, um, who I had to occasionally tell them to back up a little bit because they weren't entirely understanding the relationship between the shader and the rest of the system. Can everyone still hear me okay? Is my audio coming through okay? I'm getting all sorts of laggy things on my side with Zoom here. Zoom is not responding. Ryan or Christian, raise your hand if you can still hear me. Okay, that's fine. It looks like it's going to crash at any moment. And when it does, class is not over. Please still just stick around and come back, and I'll rejoin you in just a minute. It's definitely got the spinning wheel of impending doom here. Um, let's just go with it. Let's just see what happens, and we'll go as long as we can until it crashes, and then I'll try to pick things back up. It's a little, it's adding a little extra stress on my end because I don't know when the crash is going to happen and how bad it's going to be. But I'll do my best here. And you can just type in the chat if it's starting to the video is starting to fail or something, and we can try to reboot things and go from there. Um, anyway, so we left off talking about shaders. Um, okay, and some of the mechanics of it, and I think as part of MP3, you were asked to kind of look at some of these functions and what they were doing in practice, and maybe you've done that already. You were supposed to, or maybe you're still planning on doing that at some point. Uh, in the near future before you finally did your final submission. But these steps are kind of important. Um, the shaders that you have in your code need to be compiled in order to be used by your programs, right? It's very similar conceptually to what you're doing when you're compiling your programs in the first place, but it's something that's implemented directly in the OpenGL driver itself, right? The compiler and the linker, and then they're accessible through those function calls you have as part of OpenGL itself. And so we've seen this version of the diagram before from a little bit of just bookkeeping of the actual objects we're creating along the way for our programs and our shaders, to specifying the shader source, to doing the compiling and linking and actually using these things all together. So some things are very comparable to what we already see when we do traditional compilation. Um, we specify source. So oftentimes when we're doing more traditional compilation, we specify source as a file. And we can do that effectively here as well. We've seen a couple of different variants of how you can provide the source for GL shader source. One is just providing it as a large string, potentially read from a file. Others is providing it as an array of strings. And I saw a team that had a comment in their own code is, why would you ever implement it this way via an array of strings of different length versus just one large string associated with the source? And actually, at least in my looking at quote unquote real world usage of shaders versus educational uses of shaders, trying to explain how they work, the latter case of just having these arrays of strings is extremely more common, significantly more common, because it's very common to want to have to and to be able to dynamically generate the shaders based on all sorts of runtime considerations, whether it's dynamically determined functionality of the hardware that it's running at. That would be one reason. Just very quickly dynamically changing behaviors of a particular scene one would be interested in, versus just having this kind of explosion and growth of the total different number of files one may have to statically offline generate. By being able to dynamically at runtime generate these shaders and for passing them as individual arrays of strings, um, that allows for kind of mixing and matching of features and changing functionality in a really straightforward way. So while for us, that's not something we could support it, but that's not something we're generally supporting. Our flow, I think, for the most part, generally assumes, you know, we do this once, right? It should work for multiple passes, but I think we're generally assuming that for each invocation of our program, we have one set of shaders associated with it, statically defined, put in a file somewhere. We compile all those, um, link them all together, and then finally attach and run and execute those shaders. But in theory, we should be able to support all that kind of dynamic functionality as well. I think the other part of our problem that uh, all driver manufacturers would have to deal with, but we have to deal with our own relatively small person team associated with this course is, there is a compiler. So you've seen the script for our version of GL compile shader and what it's doing behind the scenes. It's not fully vetted, right? It's a good faith attempt at building a compiler that can do effectively just an assembly to assembly translation. Um, we don't really know if it works. So you can try all sorts of things. When you have something that doesn't ultimately work on the output side, you're testing it on the board and you're not getting the results that you see. Well, this is why we always want you to start with as simple as possible of examples, right? Get your pass-through working, get your plus 1.0 version of the shader working, and then worry about more advanced functionality. Because it is true, more so this week than in previous assignments, that if your shader's not working, it could be something that Steve and I did. It's definitely possible, and I'm never going to say it's not the case, but you need to provide some evidence to me so that I know that in fact there's a bug on our end versus it being something on your end. But otherwise, these steps are logically very similar to what we do when we're doing traditional compilation. So compile shader can return syntax errors. You have to have some hooks to trap those errors and return some values back. Right now, the little helper function we use, I think, just returns there is a compile error. You would need to explore further if you've inserted compilation syntactical errors in there. Usually, there wouldn't be an error with attaching shaders. If you're attaching one vertex and one fragment shader to your program, you're fine. But we will see all sorts of link errors, just like we sometimes do when we're, updating our traditional software programs. We're doing syntactical checks as part of that initial compiling pass. We assume that there's some other stuff, be it data, be it functions, defined elsewhere, and it's really the linker's job to determine and make those connections between stuff that's defined elsewhere and the calls to it in the code that we are currently compiling. That's also the case with our shader programs. Usually, there's less complexity, but that's very much the case. That because we have this intentionally defined relationship between the output of the vertex shader and the input to your fragment shader, the actual naming for some things have to be consistent across both shaders. So you can have two shaders, one vertex and one fragment, that syntactically are perfectly valid. When looked at in isolation, they make perfect sense. But if you happen to name the output attribute of your vertex shader something different than what the input of your fragment shader is expecting, all those compile steps will work. And then when you have a linking error, it'll usually be something pretty opaque, as linking errors tend to be, right? That something's just missing that it's expecting there. Um, in part, we get around that by, for now, doing just vertex shading and then dealing with this issue in MP4, where we then add the fragment shaders. But that will have to be the case. The output of our vertex shaders have to map to what the input of our fragment shaders are expecting, if not by position, but by name. And then for our infrastructure for the class, also by position and by name. We're using this static FIFO structure. We're not reordering attributes on the output side. We're getting input all the way straight through to output via that FIFO there. So you do see a lot of this mechanics. Yep, sure. Well, thank you for telling me. But you can hear me still? Okay, so let me try to kill this. I'm going to keep recording because I'm recording separate from Zoom here. I'm going to try to rejoin the meeting. Um, so humor me for just a minute here. Was it just now that it started to die, or has it been dying for quite some time and you just felt guilty about saying something? Come on, guys. You can tell me right away when things are breaking. How do we look now? I need at least a thumbs up again. Can you see me again? Okay, thanks. So Ryan, Christian, you guys have a lot of responsibility. I've told you this earlier in the semester that when you have your cameras on, which I do appreciate, I need to look in your face to know, so that things are still okay, that you can still see me. Now, if Zoom is dying, then your picture wasn't moving either, so I couldn't tell either way there. Yeah, and I think by default, if I have a presentation open, I think it mutes it or puts it in the background. So, and it's good to see you as well, Matt. So, Matt, give me some expressive, yeah, that's exactly right. I want to see smiles. I want to see really obvious, confused looks of something. Make sure you have this ready to go if something seems really confusing along the way. Okay, nobody watches these videos after the fact. I have the view counts on YouTube when I go through all the effort of uploading them and posting them and linking them and all that. So that's fine. So it's okay. Apologies for the technical hurdles, but the recording is actually still going here. Um, that's, I think, all I really wanted to say about shader mechanics. We do kind of hide that functionality. It's very common to have in your application a shader processing library, so you don't have to really worry about these exact details. But under the hood, that's always happening somewhere. Let's look at a shader in a little bit more detail and what that means in practice. So this is an example of very basic, kind of forward transform vertex shader followed by a very simple um, fragment shader here. But we sometimes think of these shaders in isolation, but it's always this pair that's happening here. So in this case, this isn't really showing all that's really happening here, but what we have is some incoming vertex position data that's coming in. That's our, in this case, GL vertex. There'd be some other code at the top that would specify locations and things like that. And then we would have this matrix vector multiplication here. Take the model view slash projection matrix, do all the things we were talking about last week to configure and set up that matrix to have the values it needs to have using a library or just hand coding values and passing them in, and then do that matrix vector multiplication for all the incoming vertex position data that we have. And here on the back end on the fragment shader, it's not doing anything really with that information. There's no per vertex, per fragment shading going on here. It's just saying for each fragment that we want to output, make it light gray, basically. So take a 4 vector and have it all be a fairly 3/4 of the way bright value. That would give us whatever our input geometry is, whatever number of triangles we're specifying or points, they would all be gray, independent of what we're specifying in the application. So there's nothing wrong with this shader. This shader is fine. It's also basic. The one that I know a lot of teams are playing around with is our shapeshifter. If you haven't seen shapeshifter yet, it's nothing special, but this is our shapeshifter. Let's talk about what's happening here. Um, I don't know how well that's coming across, and it's a triangle that's moving around and it's shifting its shape. This is the red pixel or the red triangle. I don't know. Maybe I should have called it the red something. For MP3 as well. This is fine. This is success. If you get this working in hardware, you have succeeded in MP3. Now, what's different about it? If we look at the code for this versus just seeing the results of it, I think you could say, well, we could have made that same exact effect with just our MP2 hardware, and you would be absolutely correct. I mean, that's 100% correct, right? You could have specified for each frame some function that changes the vertex position data and sends that over via the draw call. That would have been valid. Just like in MP1, you could have drawn triangles by hand rasterizing triangles in your code, um, in your host code, and then just sending all those points over. Right, the hardware makes it a lot more efficient to do it in MP2, and the same thing, at least in theory, is happening here in MP3. Right, for that red triangle, if for the shapeshifter code, for the actual red triangle associated with it, we're not actually changing our uh, vertex information at all. It is fixed. You could also change it as well. It's not an either or thing, but in this case, for this application, in terms of what your rasterizer would otherwise be seeing with a pass through shader, it is just a fixed red triangle. Um, I don't recall. I think it's it's a pretty small one by default. Those of you who are still having some render output cache issues, which I understand, you may want this to be a slightly larger triangle so you can, you're making sure it's not just cache issues that you're seeing when you're seeing this on the board. But it's a pretty small triangle to start, and it's a red triangle to start. So with red for just all three of our values. And then our actual draw call, the part where we say, do draw arrays, there's really nothing happening here. Clear the screen and draw one triangle here. Instead, what's changing is we have this shader that's now just not passing input to output, right? The shader is actually doing a little bit of shading, and it's meant to be kind of a toy thing. We always want to start simple and work our way up. Others have teams who have gotten to this point and have explored getting this to work in their assembly and their shader core implementation. Um, we have realized that even though from like a logic perspective, this code is really simple. I think I'm okay in saying that. In terms of the parts of your implementation that it stresses, right? When it works, great. But when it doesn't work, why isn't it working? It is for better or for worse, testing a lot of different things in your code. Even though it looks so simple, it's testing 5 or 6 different things that could be wrong in your implementation. So for what it's worth, when you get it not working, you think your core is perfect, you're pretty happy with your driver, you run this code and you get nothing, or you get something weird. Um, that's intentional, but then you really do have to start asking the why questions of, um, or the what questions as well. I guess what am I seeing? I'm seeing nothing. What debug information do I have available to me? Well, that's up to your team. How did you set up debug for this? Given some debug information, now you start asking the why questions. Why do we think we know we're getting a valid vertex input to our vertex shader core? I'm getting garbage back out, or I'm getting nothing back out, right? Why is that the case? And start asking those questions because it turns out, as I mentioned, even though in terms of what this is doing, very simple modification of position information of the input vertex. Um, to stretch, right? We take a scale, so that would be stretching our x and y. That can make the vertices move, and then consequently the whole thing grow or shrink relative to each other. And then just translating it around. That's what our plus. So times equal would be scaling it. Plus equal would then be translating it around the screen in that two-dimensional space. Even though the math is very trivial, it actually corresponds to a decent number of assembly instructions, right? So there's a lot of things going on there. And then it really does test a lot of your implementation in terms of, are you dealing with these values correctly? And we'll talk about this in a little bit, but are you actually dealing with those input uniforms as expected? Are you doing multiplication correctly? You'll find out pretty quickly if that's not the case. What I would suggest is, if you get your pass-through working, which is the default shader, if you get your MP2, the red triangle application working with your MP3 hardware in place, that means your pass-through shader is working because it is running now with the MP3 driver infrastructure. It is running that shader. It's just not doing much. In FIFO, out FIFO, just FIFO things through. Um, you're in a pretty good place, and you should be modifying this shader and testing different things to even get rid of the uniforms. Instead of X scale, well, we don't know. Is my multiplier broken? Or is my uniform handling broken? Am I not loading from the cache? I mean, there's a lot of things that could be wrong there. Change that to a constant instead. And then that lets you know, well, at least because it's a constant, my multiplier is working. And other things that you can test by modifying this that doesn't require a new build of your bit file, that doesn't require lots of modification to your OpenGL application, just by changing this file, making backups of it and whatnot. But changing this file, you can learn a lot. You can answer a lot of those why questions. You're probably going to have a lot of tabs open. It would be this file, your Vivado window to reload and grab ILA data. You probably also want to be looking at the assembly output of the new shaders that you're modifying to get a better feel for, well, what parts of my implementation in Vertex Shader Core is this stressing? It's a deep debugging process, but there's a lot of, even for this simple one, the red triangle equivalent for this assignment, there's a lot of things that could go wrong. And so you want to be in a place where you can test a lot of things for every given bit file build versus that miserable experience of every idea requires a 1.5 hour bit file build, and you won't know until tomorrow morning whether this idea you had at night is actually a good one or not. Um, but anyway, this is our simple example of our simple shapeshifter with a vertex shifter shader here, and it's using some of the features we'll talk about here. In terms of what then actually happens in our OpenGL code, again, our actual input Vertex buffer data doesn't change at all. We actually just send that data through once. We don't modify and copy that data. And then at runtime, we're specifying those uniform values, those per draw constant information that we provide as inputs to our shader to be able to do that math on a draw by draw call basis. There's no requirement you change those values on every draw call. Some of them could truly be constants. You set them once and completely forget about it. Others you want to change as frequently as every single draw call. Others still may change relatively infrequently, but more than once per execution. And so we have those hooks to both be able to recognize where in my shader, this is a linker issue again, where in my shader are these variables defined? Get a pointer to them, or it's via some record ID, but get some metadata associated with those individual uniforms, and that's what's happening here in my code. And then have a call that allows me to update those values based on whatever logic I have in my application. That's gonna be per draw call. And one final point about MP3 before we just continue on with shaders here. MP3 is turning out to be a cache assignment. That was not my goal for it. The actual fetch, decode, execute isn't too hard, depending on how much special functions you want to also implement. But we really have to think much more carefully about the cache in MP3. I had thought I had put together a good cache organizational document, but I didn't. So we have bonus point criteria for MP3, which is clarity of implementation and documentation for MP3. A nice tight here is how, for future students of the class, you interface with the cache design that's provided for this architecture would be worthy of at least a decent amount of those points because we're doing a lot now of reading and writing to the cache for data, reading to the cache for our instructions, and to even support this, you can't ignore flushing the cache anymore. We are pushing those values into memory as we implement that call in our driver, but we're interfacing via a cache. And there is no cache coherency logic that can automatically detect that a write to the backend location got updated. There's no volatility check or anything like that in that cache. We have to be the ones that provide that information. That first time you drew the red triangle, here's what the values of uniforms were. There was a cache miss. We grabbed the values from memory, put them in the cache for those 4 floats that we have here. Second time around, these values have changed. Our program doesn't know that. Our program running in the shader has no way of knowing that those values have changed. It doesn't have any state. That's either the downside or one of the beauties of this kind of stream processing model that we're doing here. It is a very simple input to output processing machine, right? It gets a vertex, it transforms that vertex based on the code associated with it. We now know because we are doing this hardware software integration that those uniforms that are in the cache are we don't actually know if they're wrong, but they're potentially wrong. They're potentially stale. They're potentially old data. So you may get a vertex shapeshifter application that shifts it once and then everything is solid. And that's at least you know exactly what the issue is if you're seeing that. That would be a cache issue. We would have to flush the cache or have some very simple way of invalidating the cache. You generally, because we are only updating the uniforms once per draw call, you generally would only have to do that once per draw call. But then likewise on the instruction cache side of things, in theory, we can be changing our shaders all the time. We can change our shaders for every draw call as well. In practice, we probably won't be doing that. I think our infrastructure would work if you try, but I think in practice for the kind of things we'll be demoing, you'll have one set of shaders per OpenGL application. But that cache, because we're using all the same instruction memory addresses, will be caching old shaders. So until you get that sorted out, you definitely have to be reprogramming the bit file and resetting your cache every single time you are loading a new application. Because otherwise, what will happen is you will be making some changes to this. You'll be running your new OpenGL code given some significant or even trivial changes to this, but your actual Vertex shader core, it would be extremely hard, Brian. I mean, unfortunately. And I've thought about it because it would be coherency between that cache and the backing memory controller, which has no concept of that. If we had 2 caches and we were worried about that, or a first level and a second level cache, there's things we could do. Even Xilinx IP provides some ability to do that. For this, I don't think we could do it. I don't know how to do it, and so we have to at least flush the. That's the solution I know of right now would be to flush the cache when that happens. Um, but as you make your changes and you're running your new OpenGL application and you're testing things and you're pretty sure your hardware is working, well, the compiler, what is it doing? It's checking syntax, it's converting to some binary blob format that we've defined, and it's pushing that to our data memory, pushing it to our memory, right? Our DRAM in our system here. The cache, for the same reasons, has no idea that anything has changed. So you'll be changing code, and you'll still be running your old code because even though the number of instructions we're emitting, not a trivial number, but it's measured in the tens and twenties and maybe a couple hundred instructions. It's all going to fit in the cache that we have defined for this. So you have to flush that cache. Probably at the very beginning would be a safe place to do that of your driver of an initialization place. You can also, I think, flush your cache every time you see a GL use program call, which there has to be one. Maybe not. Okay, yeah. There has to be a GL use program call in your code. The problem is, I mean, that to me, that's the correct way um, to decide when to flush that cache. When I see use program, that means we're telling the hardware you have a new program coming in. The problem is in some of our implementations in the OpenGL side, we have that GL use program in the main draw loop. It's not supposed to be there. Your driver then has to be clever to know. Uh, I called GL use program with the same program ID twice in a row. I don't need to flush the cache anymore. So there's a lot of different ways you could do it. Different trade-offs between strict conformance with what we intended and what OpenGL says is allowable. But you have to be aware of that issue. So we can't avoid that issue any longer. In render output, we had a cache that you should have been flushing there as well. But if you didn't, you just had kind of crummy looking triangles, at the very last few fragments for it. This will not work if you're not taking care of the cache. Okay. That was my final thing about MP3 today with regards to that. Let's talk a little bit more about what you can do with your GLSL syntax here. It's this very C-ish kind of syntax. To me, the nice thing about it, maybe this is nice coming from a C programmer's perspective. If you're using more reasonable and modern programming languages, this isn't seen as an especially novel thing. But having these vectors and matrices being these kind of first class objects in the language is, at least to me, a very nice thing to have. Where um, as a C programmer, one either finds a good library and sticks with it, or you find yourself re-implementing very basic matrix vector, manipulations over and over and over again, um, for better or for worse, right? With all the mistakes that come with that, all the little weird one-off errors that, unless you really know your data, are very hard to track down. Well, having these matrix types and these vector types as syntactical features directly supported through hardware instructions in the language itself means you really don't have to worry about hardly any of that anymore. So you have your basic types, the kinds that one would expect. I don't know what our compiler does if you specify anything as double, so don't even try. But otherwise, your vectorized types are provided there. So by default, if you don't specify a type qualifier, they're all floating point. I believe they're all single precision floating point by default. And that's where you get your vec2, vec3, vec4s. And all the matrix types one would generally need to assume that you would have for doing graphics processing. So that's why you see matrix 2 up through matrix 4 and a couple other edge cases there, but you're not going to generally need to see arbitrarily sized matrices in the language themselves because the type of data we're processing tends to be of this 4 wide dimension. So you're fine keeping these matrices also of that size and limiting our vectors to that size. We'll talk a little bit more about that syntax. We've already been seeing that with regards to accessing individual elements of a vector. Programming languages, people have lots of strong opinions about what is the quote unquote right way to do things, and I don't really know. I mean, it's whatever you become comfortable with. For me, maybe it's because coming from a C programmer, when I see something as a 4 wide vector, using the array syntax is the logical way for me to work with it. We see this in our VHDL code, right, as well, right, where we have a few different options, how we want to implement these attribute types in VHDL. It's the same thing here in GLSL as well. For me, if I have a vec4, think of it in terms of 0, 1, 2, 3. It's just a very natural way to deal with the data. Code just seems easier to write. But when we are thinking of attribute data that actually has really precise meaning, there's an argument that thinking of it in terms of that precise meaning leads to easier to read code, which would then be using that kind of subset operator for your positional data, or for your color data, or for texture coordinate data. It's all referring to the same exact thing, though, for better or for worse. So if you're worried about what the first element is in my vec4, you can use .x. To me, that only makes sense if you're working with positional data, but you can also refer to it as .r. That's the red channel, but it's just the first element. It's of 0. It's the first element in that vector, or you can also refer to it as .s. They're all equivalent. They all assemble down to the same exact assembly instructions for accessing the first element in a vec4 here, or in a vector type that you have here. And the reason I don't especially like using those, although there's some cool things you can do with the swizzle operators and whatnot, is that once you then get to matrices, you tend to see the array indexing anyway at that point. So if you're already doing that for your matrices, to me, maybe again coming from a C programmer's perspective, that's the natural way to access multi-dimensional data is via the array operator. But they're both valid. We should be able to support both um, equally. And again, the big picture here is that by having these as these kind of first-class types, you have all the arithmetic and the logical operations well defined. That should definitely simplify the code. The lines of code you would require for GLSL is significantly lesser than if we just said implement this kind of thing in C, where you'd have to do all the for loops and all of the dealing with allocation and the like. You don't have to do any of that with your GLSL code. We have to be careful with our storage qualifiers. We've talked a little bit about uniforms. Those are different than constants. Constants are literally constants. Those are compile time constants that you can assume certain optimizations are going to happen with them. That is in comparison to these uniforms, which are also constants. Those are per draw constants. Um, so that allows us to manage the memory for them a little bit differently than if they're just variables. But that then says that for a given draw call, all the invocations of your vertex shader or your fragment shader, which can be done completely independently of each other. For us, they're not. We only have the one core. But there could be hundreds or thousands of them being launched, or tens of thousands of them being launched at any one given time. They would all be assuming and accessing the same exact data for them. Your cache, such as we have, should be an extremely high performing cache for your uniform data type, because it changes once per draw call. When we think about the performance of what's happening here, for our shapeshifter code, as the example where I'm mentioning that, our vertex data doesn't change at all for this code, but our uniform data is changing for every draw call. We won't see any performance benefit for MP3 in doing that. And that's not because we just have the one vertex shader code. We'll see no performance benefit because we're sharing nearly as much data or updating nearly as much data per draw call as what we would be doing in the MP2 version of this code. If I asked you to write this code using your MP2 hardware, you'd be updating 3 vertices each draw call. So 3 XY values. So you'd be updating 6 floats somewhere in memory, right? Is how you would do it. Whereas here we're updating 4 floats in our uniforms, and then we're potentially flushing a cache as well, right? Not going to be more performant for that reason. But the idea of having these uniforms is that because they're only changing once per draw call, that can become very meaningful, as opposed to having them be some attributes that are constant across the entire draw call, which would be the MP2 approach to doing this same exact code. For one triangle, the benefits are very minimal or negative benefits for doing so from a performance perspective. But this same exact code that we're calling shapeshifter, that's one moving red triangle with no change at all to my shader code in this stream processing model of computation we have here, could very easily have been 10 million shapeshifting triangles, right? The only difference would have then been the number of triangles, the number of vertices we're specifying initially, and the draw call that's telling it how many are to be drawn for that particular draw call. The uniforms could then, at least in theory, be constant across all those invocations of the shader. So that's what we refer to as kind of a constant type. It's constant per draw call. It should, in a more general case, correspond to a lot less data having to be trafficked versus all the per vertex data that we have to generate in the first place. It's just that for this application, we don't see that because we have one triangle with one set of uniforms, and we're updating the uniforms as frequently as you would have had to have updated the attributes in the first place. So there's no performance benefit here. This is as slow as your MP2, maybe a little slower than what your MP2 equivalent would be. But you could very easily change this to be 500 red triangles with just a single time initialization of what their attribute information would be, as well as then now uniforms that could be constant per draw call. And you could very easily build all sorts of different um, position and scaling and other kind of things. You know that one asteroids example from MP2, the cool demo we had for that. Depending on how much of that logic can fit into the structure for our shader architecture, you could provide as input just some basic parameters to the current game state. Here's the timer. There's a global timer that you're updating each time. Maybe there's some other state that's per object, and then in theory, then you could have just a statically defined set of geometry you're specifying, and then it's just the uniforms that would be changing on each draw call. If your logic allows that to happen, that would be significantly more effective than having to recalculate all your geometry when your game state changes. So that's constant versus uniform, and then we have our in out. That's our that's our per vertex or per fragment uh, shader global variables, and those are the ones that we would then have to, if we're writing to them for the input side, we have to specify that location to be bound in our OpenGL code. In and the out qualifiers are not new. If you look at GLSL code online, you'll see a lot of these older examples that use attribute as in and varying as the output type. They refer to the same exact thing, and for the most part, um, in my experience, it seems like the GL compile shaders, even if it's specifying a more modern version of OpenGL and your driver and GLSL, it can handle the old versions of that as well. It seems to be able to figure out what needs to happen there. Um, that is still a little bit of a minefield, and so the correct way to do so, and you'll note that we try to do that, is to be very explicit about what version of the language you're supporting in your shader. That kind of stinks, in a lot of ways, right? The language should be the language, and the driver should worry about versioning. But in practice, that's not the case. So we've been roughly targeting OpenGL version 3 with some version 4 features. And so syntactically, you're pretty safe if you keep this at the top of your shader codes that you are developing this semester. Our infrastructure should be able to support everything that happens inside there. And then finally, although none of the demo examples we've been providing have been doing that, you also just have general read-write buffers that can be provided, and that's effectively passing a pointer to the shader. So that would require some additional shader state. Generally, it makes a lot more sense when we look at the compute side of things, where as part of the shader state or the compute engine state, we have this concept of here is the relative ID of the shader invocation that we're currently executing. So they're all independent of each other, but they have some knowledge of where they fit amongst the whole. But at least in theory, that's something that should work for MP3 as well, that you can specify basically a pointer to your shader for your vertex shader, and you can then render to that buffer if you want to, right? As opposed to just generating output vertex values, which you still are required to do. You can also then update arbitrary regions in memory. So you can break things really badly if you want to and have some fun with that. But that, at least in theory, allows you to do for my incoming vertex. Oftentimes this makes more sense for the fragment side, but for my incoming vertex, I'm going to both transform that vertex and I'm going to update some value in memory corresponding to some information that's relative to the vertex. We're not going to talk about that much this semester, but that used to be the way we would do GPU compute before that was even really a term. We would be basically tricking the hardware into thinking it was doing graphics rendering, when in fact it was actually doing computation. And it wouldn't actually correspond to anything interesting in the actual render output buffer at the end of the day. It'd be garbage or kind of arbitrary data. Likewise, on the input side, your geometry wouldn't really correspond to anything that's visually interesting. It would correspond to data that you wanted some processing applied to it. Nowadays, we don't have to do such hacks, but that was, if you see the term GPU used, general purpose computing on graphics processing unit, that's what that's generally referring to. That kind of tricking the GPU into doing compute when it wasn't intending to do so. We don't have to trick it like that anymore, but you can, and even in MP3, you should be able to. For one of the teams that mentioned that they want to do unified shading and some compute side of things, probably can do it already. It's probably already there. Maybe there's some work required to make sure the compiler does what we would expect it to do, and that the driver is supporting that in a way that makes some sort of sense. But I have this feeling that it already should work, because ultimately, this is a little processor, this shader, that takes assembly instructions defined in an ISA and has an ability to do loads and stores. We don't support much in the way of branching, um, but there's all sorts of things you can do with just a single stream of computation, right? You can always, if you have a loop, you can always unroll all your loops. You can get rid of branching via extra special function units and extra ways of emitting, code and making it maybe slightly less efficient that way. So I have this reason to believe that I think we can already do compute. I haven't tried it. I haven't played with building a shader that does some molecular dynamics simulation or anything like that. But in theory, takes data, does computation of data, outputs data to a buffer. Somewhere along the line, some other piece of code has to read that buffer and do something with it. All those hooks should already be in place. So those who are interested in the compute side of things, I would focus maybe on one type of application to implement. You should be able to get it working. I think it's very doable. It's not a stretch. Back into the syntax, all of your C style operators work as expected. And I don't know for this class if I have to really say anything other than that. Um, Likewise, the constructors for the built-in types or for structures that are also supported, they generally work the way you would hope they do. I think that's how I would describe what's happening here. Um, that if you want to initialize a length 3 vector, you can do so by passing it 3 floats. And that's exactly what's happening in this first example here. So that's what I mean by it kind of works the way you would hope it would in terms of more sensible languages. If you've worked with NumPy and Python, it's very similar in terms of initialization of vectors and matrices. Um, it's a very MATLAB-y type syntax as well. So it's all very similar. There's only one set of ways that people generally like to be able to do this kind of thing. But that so it initializes vec3s the way we'd hope they do. Likewise, it can compose as long as the left-hand side equals the size of the right-hand side, you get exactly back out what you would hope to be the case. So all this example is showing is, for whatever reason, and this is arbitrary, I have a vec2 that I initialize, and then I want to initialize a vec4. I can use that vec2 in there, right? And it works because we get 1, 2, 3, 4 final components back out. So don't overthink those parts. It generally will do what you kind of hope it will do, both for the array indexing and for the construction of these objects. Sometimes type conversion is a little bit less obvious than you would hope. It's not using casting, which is generally considered to be a bad idea anyway from a programming language development perspective. Instead, having explicit conversion functions from one type to the other. Those of you who now have become so much more familiar with VHDL than you were before coming to the semester, that shouldn't scare you at all. I mean, I've seen some code that had like 12 conversion functions in a single line of code just to kind of get it to work. And um, usually they're not all needed, but I understand why at 2 a.m. in the morning why that seemed like a good idea. Um, some of you have already been playing around with the swizzle operations. And what, as I mentioned, what generally happens is for these GLSL vector types, you'll find that occasionally or maybe often you may also want to access the components within the vector as well as potentially operate on all of the components at the same time. So we support, or GLSL supports for that reason, the normal C vector accessing using that square bracket notation, right? A of I is something that is supported here with C style zero based indexing. Um, and then additionally, the vectors, but not the matrices, support this idea of swizzling, which is, at least in theory, it allows you to access the components within that vector by a particular name. So, for example, that first element in the vector could be element of zero, but it can also be referenced by names either .x, .r, or .s. They're equivalent naming conventions here. And the idea is that you have those different naming conventions, the XYZW, the RGBA, or the STPQ, to help clarify their usage. That when you're using RGBA, um, it's something of a signal in the code that you're referring to color for that particular computation that you're doing. Likewise, when you're using STPQ, you're referring to texture address calculation. And when you're doing XYZW, referring to the position either of the vertex or of the fragment. And that's one reason that you see these operators in use. The other reason is this ability to kind of natively swizzle or replicate components on the right hand side of an operator or on the left hand side of the assignment operator here. And that's something that, at least as a language, other languages do support this, but as a language, C certainly doesn't support, right? You cannot do in a single line of C, I want to assign array A of I to I plus 2 or something like that. You can't do that in C. A lot of other languages can do that, but you can't do that in C. So if you want that kind of functionality, these operators can be quite helpful for reordering elements in a vector, duplicating, replicating elements inside a vector. Basically, if the left-hand side is the same size as the right-hand side, anything is fair game in terms of the combinations here. So that's kind of what we're seeing here with this example. So um, this would be initializing the vector to all 1.0. This example is again our vec3 initialization with three just different floating point constant values here. And it would be just explicitly setting that for this 4 vector, we're initializing the .x to the .y and the .z in that order of those values. It also could have been .zyx or it could have been .wxz. The order is independent. It gets compiled down to, it gets assembled down into effectively the same as the array indexing for it, but allows you to do that in a single line of code. Likewise, in a one line, you can reverse the order of the components by just specifying w.wzyx is equal to foo, where this is kind of implied that this is foo.xyzw. You could be explicit and write it as well, but by default, that's assuming the regular ordering on our right-hand side here. So that is kind of useful. That allows you to do all sorts of replication of components on that side. It's sometimes hard to reason about why for any particular type of swizzle operation you may want to have it, right? Why would I want to reverse it? It's a valid question. Why would I want .xxyy? What am I doing with that data? And we will see some examples, but we can calculate the total number of permutations here. There's a lot of different permutations. Some are a lot more common than others. It is extremely common to just grab a single element. That's an extremely common operation. Doing .xxyy is a less common operation here. Then when you have your matrices, you can then grab individual values of the matrix as needed. Um, this would return back a vector. This would be actually the first column of your matrix of 0. This would be the first column, first row of that matrix to return a single floating point value back. So I think it's all reasonable. I think it's all logical, at least in terms of how it was created, what you can do with your matrices and vectors. If you have a question, can I do this? The answer is generally yes. You just got to find the right exact syntax for it. There's a small gotcha here, and I think it's a small gotcha. I don't think it's going to affect us too much. Well, so for the driver, you do have to implement the function that initializes matrices, right? The uniforms. So this comment should give some of you a little bit of heartburn, potentially. Foo equals my matrix of 0. First column of matrix is what's returned back as our vector. Because it turns out the ordering of it is exactly the opposite of what C would be doing. It's column major order. So the matrices are stored column by column and not row by row. I'm sure there's a good reason for that. I don't know the good reason for that. I frankly don't have a clue why that's the case, but that is the case. And so you may find that your matrices are accidentally transposed because if you're initializing them in hardware, you have to be very careful. The assembly that's getting emitted by our compiler, by the SPIRV compiler, is assuming, as the language specifies it, that our matrices are ordered column by column and not row by row. The reason it's not that big of a deal is because for the same reason, the library that I would expect and want you to use, that GLM library, and it's extremely comparable, right? Also is storing the matrices column by column. So um, as long as you're consistent in terms of using that library and then writing your shaders accordingly, you may get it wrong, but you won't get it wrong twice. You know, you'll get it wrong on the GLM side, and then your shader will work exactly the way you would expect it to. And likewise, then for your driver, you have to be aware of that. But it's possible, depending on the function that's being used. Um, Depending on the function that's being used, you have to watch out for that. How you're traversing the matrix that's being provided in that uniform call that's being provided there. So instead of storing it vector by vector, it's storing it attribute by attribute. I don't even know if that's the right way to think about it. I understand your question. Usually, our use of matrices is different than our use of vectors, right? Vectors are referring to attributes generally, right, or variables that are associated with um, with attributes. That's what our vector data types are for. Whereas matrices can be used for all sorts of reasons, but generally referring to the transformations to be applied to those matrices. So it's not that clear, what you get by having it be column by column versus row by row. We didn't go into that much detail on it, but the last column of our model view matrix is the translation amount, how much I want to move in the XYZ dimension. So I guess there's some value that you can specify matrix of 3, and then that's your translation value. Um, but that's a very modest thing. That can't be the reason why it's done column by column order. As long as you're aware of it, you can work around it. There's some good discussion about cache coherence here. Yes, lifted is not correct, Matt. I don't know what you're referring to. So this was open source extension of the cache controllers that are there. Xilinx provides their own cache IP as well. You're welcome to give that a try. Significantly heavier and not open source for how they do their caches. So I like these better. We'd already talked a little bit on Tuesday about the different control flow um, and what it's provided. The limit, I think, from our perspective, is right now you look at the ISA and we're not doing that. So you have to kind of limit what you're doing in your shaders if you expect them to work. A lot of the simple control flow can be replaced with special functions that effectively calculate what the result of that control flow it would be. So we would have a couple examples of that. A big one could be for certain types of fragment shaders would be discard. That's kind of killing the current fragment. Just stop execution. Don't actually output a fragment for that particular shader. And there's all sorts of reasons we would want to potentially do that. There's all sorts of effects that come into play by only drawing a certain subset of the fragments that are potentially rendered at the output of a triangle. Function calls aren't terribly interesting, other than even today there's still limits on what type of control flow is possible. So don't build something recursive. There's not really stacks in your implementation of a vertex shader. There could be, but I think by default we assume there's not. So I think recursion is allowed as long as it's a uh, compile time amount of recursion versus an arbitrary amount of recursion. Likewise, we have these functions to allow for composability of our shader programs. They're not real functions in the sense we think of them as functions. They would all get inlined by the compiler anyway. So there's still functions from the programmer's perspective, but there's none of this concept of for shader cores this like procedure call interface and binary compatibility between different functions and things like that. None of that is a design consideration for this. There's no ABI for shader code in this sense. There can be at a higher level of abstraction, but once executing on the shader, we're not worrying about function call overhead and things like that. So you have the ability to do it. It's a programmer feature. It doesn't actually save you lines of assembly code and performance at all in your actual execution of the shader. So let's talk a little bit more about some of the built-in functions here. Um, there's a lot of them, and they're kind of fun to read up. Sometimes you can read this and you get a good refresher on freshman year trigonometry and remembering what some of these operations are supposed to do. But at least it does all the things one would assume by default. If you've used MATLAB or NumPy and Python, you're familiar with these kind of operations. Scaling by a constant, so that's an element-wise multiplication is allowed. Component-wise addition is allowed here, where you're adding two, three vectors before together. Also, component-wise multiplication. Different languages have a different syntax for component-wise versus dot products, and GLSL is no different. And I think most importantly, from our perspective, is the very basic type of linear algebra we assume is necessary to do viewing and transformations in the 3D space is just natively supported by the language and generally natively supported by the underlying ISA corresponding to the shader code itself. So matrix multiplication, whether it's encoded emitted as a single instruction or a relatively small number of instructions, it's directly supported in the language itself. Likewise, matrix, vector, and depending on what your needs are, vector, matrix. You always have to be a little bit careful, right? Because the order is relevant. It's not order independent once you're dealing with matrix types for doing multiplication, whereas for your scalar types, it doesn't matter at all. So there's some bugs that sometimes come into play. You'll read lots of forum posts about why is my transformation, why is my triangle disappearing again? That's a common bug that people sometimes have. Um, a lot of the basic trigonometric functions, if it's in your graphing calculator, it's generally supported in GLSL. I think that's a good way to think about what things are supported. And generally, although not documented as such, generally supported natively by the underlying hardware. In the graphics context, as I've been mentioning, you will not find that documentation. But when we look into CUDA, and if you open up the several hundred page, CUDA programming guide, they will be much more explicit and tell you, specifically, uh, there is a sign instruction and a hardware supporting sign, and it will take 8 clock cycles. It'll even tell you generally for a given class of hardware, here is the performance overhead of doing this type of operation. So we can assume there's something very comparable on the graphic side because it's using the same exact hardware. And in general, you can assume it's in your graphing calculator as a built-in function. It has a GLSL equivalent for doing the same exact type of mathematical work, and it generally would have direct hardware support for doing that efficiently. Uh, Not as efficiently as doing things like addition and multiplication, for the same reason that you're going to be seeing as you start to implement this, in your MP3 code base, right? Um, you can implement a sign function. There is IP core. There's well-established approaches to building hardware implementations of trigonometric functions. To do it properly may take you a while. So if you use an IP core, you're probably better off. But the hardware exists to do such things. It's generally not as efficient. There's generally different trade-offs involved in doing addition. The complexity of doing sine of x is much more complex than x plus y, right? So you have those cores there, and in modern hardware, there is function units associated with that. But usually, there's different trade-offs associated with either the quantity of those things available for you in your hardware, or at least the performance associated with them. So I always want you to not really think of it in terms of, well, there's a sign function in hardware, so it's fast. Well, fast is relative. It's probably faster than a software emulated version of the same, but that doesn't mean it's as fast as you need it to be. Just because something is in hardware does not make it fast. And any of you interested in doing, graduate projects in an area of doing reconfigurable computing or hardware design, hardware is not magically faster than software. There's no magic mechanism by which that's the case, right? It's always a matter of understanding the trade-offs between what is the software doing in my system, 'cause there's always software, and what performance needs I have for that sign function. So it's not a question, is my sign function in hardware fast? It's really, is it fast enough, for the needs that I have for a particular application? So you'll see different latencies at the very least associated with it. If you configure an IP core in Vivado to do Cordic or other ways of implementing trigonometric functions, you'll be able to play with those trade-offs. And there is no one correct answer. Even for the divider core, you can see that when you configure the divider core for MP3. There's no one answer, but there's a design space you get to explore of how much do I care about the clock frequency of the entire design? How much do I care about the total amount of my chip area dedicated to this individual special function unit? and then how much do I care about the latency and or throughput of this particular special function unit. Um, and it's a design space that one gets to explore. We could spend a few weeks just doing that for sine of x. There are a lot of approaches, and none of them are new, right? Because being able to implement sine of x in hardware is not a new problem, right? It's not a new consideration. As soon as computers were built, we wanted to implement trigonometric functions on them, and even so-called software-based solutions, in which sine is just a function call in a library, use very similar approaches. So that's another reason that hardware is not magically fast, right? Anything you can do in hardware, you can write a piece of software to do the same exact type of steps of computation. The question is how fast those steps are, how well do they map to native hardware versus building something directly in hardware. So for sine of x and for all of these functions, part of it is why I didn't want teams to kind of dive into that to begin with. They're interesting. Each one of those could probably take you 2 weeks to do properly. So we have to just kind of pace ourselves. We only have so much bandwidth to work on things ourselves this semester. There's lots of good papers to read, uh, uh, applied math to kind of consume, software implementations to look at, hardware IP cores to take a look at and play around with. There's a lot of things to explore for each and every one of these. They're not magically fast because they just so happen to be in hardware. It's part of a design space exploration for the particular chip that we're worrying about. From our purposes, for our design space exploration, we're going to be pretty happy if we get this working. And then all of these, and there's a whole bunch of them. And I think one can kind of lose sight of that there's 13 boring instructions and 45 interesting instructions from a computational perspective. We just do not really have um, the bandwidth to do the interesting ones this semester. Um, that's also a possible project idea. I think for that to be something a team would work on, you'd have to have a compelling application. Here's an application that the shader would be really cool. We'd be able to show really cool effects, but we can't get it to work because it does require, and there's no workaround for using all these special functions. And so consequently, we're going to implement a few of them and show that, we're spending more hardware on the problem, and we're getting really cool results that we couldn't do otherwise, or couldn't do as effectively otherwise. Um, Ryan asked about analog hardware, and that's very much the case. I don't want to get into that. I mean, analog is significantly more powerful than the digital computing that we use on a day to day basis here. It's also a lot harder to deal with. That's a much bigger topic. Again, every function that one would expect you to have on your graphing calculator is supported in GLSL. So your powers, your exponents, your natural logs, your square roots, your inverse square roots. I was just looking it up that if you look at the most recent CUDA guide, it says inverse square root, and I don't have enough intuition to know exactly why, is roughly 4x the cost of all these other instructions. So I just got to think about that a little bit. And again, there's a mathematical reason for it. I just don't know the reason why inverse square root is worse performance wise than just regular old square root, or worse than log. Um, there's a reason for it. I don't know the reason. But that's something that in the CUDA and compute side programming guides, they will lay out what the relative performance is of these things. You can also relatively easily write micro benchmarks to kind of infer what the performance would be of these individual special functions. So you also have absolute value and the sign, so returns -1 or 1 for the sign, and your min max and clamping functions there. Um, Also, a very common things that we want to be able to do when we're dealing with shading, because we do know that ultimately we're shading, right? We're ultimately calculating color. No matter what we're doing with shading, we care about the color of a fragment in our color buffer. So knowing that there's a valid range and restricting within a valid range is a very common operation we need to be able to do in our shading. So it's supported natively via instructions, some of which would be easier to implement than others, right? And so there are all sorts of tricks that we could once do um, to get rid of what may be relatively cumbersome or requiring more branching than we would want. Uh, GLSL at the assembly level with what the underlying core could do using some of these special function units. So that leads me to what I think will be our last exercise today. So I don't think we need to break into groups. Maybe if we try this again next Thursday, we can break into groups at that point. But given the time that we have remaining today, let's take a hack at this. So take a couple minutes and you can hopefully still see my slide here well enough. Given the functions on this slide, though, so that's the direct hint. Um, where we have functions for the sign, the absolute, so these absolute value, sign, min, max, and clamp, right? Where clamping is, it's clamping operator, right? Keep within that range. No matter what x is, make sure it's never less than 0 or greater than 1.0. Can we replace both of those GLSL snippets with just a single function call? And likewise for the one below, can we do it without needing any of those branches whatsoever? I'll give you just 2 minutes here, and we're not going to talk about analog hardware in this class, but take a moment and think about these two exercises. I was trying to find while we were working this a good recent decent paper of a student of mine where we were looking at various trigonometric functions and how to best implement it. It's a very fun topic. It's a well explored topic though too. So you have to be really careful when picking that as if that's an independent study or a graduate topic to do. Implementing sine of x efficiently, because not only do you have to look at what's recent and what people have been doing on modern FPGA platforms and the like, you actually do have to look back at what were the folks in the 1950s doing. They also had to look at these same exact issues. They were probably smarter than us as well, right? They had to deal with more constraints than we have to deal with today. So that's a tough problem for that reason. That you have to look at papers that aren't digitized even to really make sure that you're not just reinventing the wheel here. But it's actually a pretty fun area to work on because it's a well constrained problem of I know exactly what my input output relationship would need to be. I can tolerate some amount of error in the output computation potentially, depending on the use case for it, or I need to make spec, which would be matching what a software implementation with IEEE 754 would give you. Um, and then you have a design space to explore, which always makes a nice kind of self-contained problem to work on for an independent study or a creative component or something like that. It's challenging only because you're not the first person to think of that idea, so you have to be very careful and really seat what you're doing with the rest of the academic literature. So Ryan, by the way, a lot of these approaches are iterative that start with a good guess, that start with a lookup table. You can't, for floating point, you can't do a lookup table. Well, you can, but it'd be exceptionally large and not worth the trouble, right? But in theory, right, everything has a lookup table. If you have a 32-bit input, that's 2 to the 32 values in your lookup table, and you have the answer there. Now, when you have two 32-bit issues, that becomes a bit intractable. But oftentimes, what a lot of these approaches will do will start with a lookup table based guess, and then there's various iterative approaches that get you after. Someone mentioned power series. That's basically what a power series is doing, right? You do your Taylor series and whatnot, and then you start with a good guess, and then you converge to a reasonably correct result with a certain bounded error amount. So okay, those are all fun projects. You don't have the bandwidth to do this with your class this week for MP3 for any of those. Um, if you find the right IP core and you try it out and it works, or you peeled off one person from the team and that's what they were exploring this week, that's perfectly fine. Uh, get A plus B to work before worrying about A to the B. Um, so for this one, for the first example, any thoughts on how we do max, the min of the max, with a range of a minimum value defined and a maximum value defined? what we can think about this is I don't know about 2.0 clamp. Well, I see what you're getting at. It's not rounding or this one down here. So these are two different examples here. So for the one down here, 2.0 times round of clamp of x negative 1 1. Not quite. We have to be a little careful with that. But for this one up, you're very close, but it's reasonably close, and I appreciate you trying something, Matt. For this one, right? You would work inside out, right, for the function calls. So you would have we're taking the maximum of an input x and a minimum. So if x is less than the minimum, we set this to be the minimum. Likewise, if the result of that happens to be greater than the maximum, we set it to be the maximum value. So we're guaranteed to be greater than or equal to the minimum, less than or equal to the maximum. So this actual implementation is exactly what that clamp operation would be doing. So it'd be a clamp of x with minimum and maximum. What about this second example here? And then I'll let you guys go for the day. What can we do for this example? If it's greater than 0, the value is 2. If it's less than 0, the value is negative 2. That clamp example is kind of close fun, but we don't actually need to do it. There you go. So thanks, Micah. So that's specifically what that sign function, um, maybe signum function, whatever you want to call it. That's the actual sign sign of the value. Gives us -1 when it's negative, +1 when it's positive. And the reason I added that little comment this morning when reviewing the slides is this otherwise does not work when x equals 0. But if x is greater than 0, the value is 2. If it's less than or equal to 0, or less than 0 because it's not equal to 0, the value is negative 2.0. So we would just take the sign of x, sign of x, and multiply by 2 to get that value. I did tweak that part right there because I realized that was not correct otherwise. Let's leave things here for today. Apologies for any of the Zoom issues we had along the way. I expect to see some push. I haven't seen it yet for MP3. So I know it's been a grind this semester. This class hasn't been a grind the last 2 weeks, I don't think. So now it's time to start it up again. You've given your time and your energy to your other classes. You're getting great grades. Your family's gonna be so proud of you when you graduate and all that. But for this class, let's get MP3 working. It's very doable. Um, I mentioned earlier in passing that this assignment is turning into more of a cache interface assignment than I expected it and really thought about it to be in the first place, but it is. The actual logic for testing individual instructions, most teams should have already working or close to it. Now, how do we get the whole big picture to work together? Start simple, add complexity slowly, test as much software as possible for very minimal hardware tests, as always. Let's leave things here for today. Excited to see what you come up with, but gotta push on it to get anything done. So I'm looking forward to seeing everyone on Tuesday with your demos.